class, welcome to lecture 26, and in this lecture we're going to talk a little bit more about some topics related to atmospheric chemistry and also take a look at a fun little topic where we see how meteorology can actually relate to the field of urban planning and to urban development. So that'll be something that we'll talk about towards the end of the lecture, but for now we're going to finish up the topics on atmospheric chemistry and some of the consequences that we can see in the atmosphere that are related to the concepts that we're about to discuss. And the first of which concept we're going to discuss is the idea of chemical kinetics, which basically is the branch of chemistry that deals with the mathematical modeling of chemical reactions that are frequently performed. And one of the more fundamental aspects of this, we're not going to go into some of the more elaborate details. This actually can get very complicated very quickly, but for now we're just going to cover the basics. One mathematical expression that we're going to be primarily working with during the course of this lecture is going to be the one that you see on the screen here, where the rate of a chemical reaction is equal to a constant, and in fact this specific term is referred to as the rate constant, this lowercase k, times the concentration of one reactant to the power of its coefficient, its reaction coefficient, and we'll see an example of that a little bit later on, times the concentration of another reactant, again, that concentration raised to the power of the coefficient that appears in front of it in the equation, the chemical formula, and then you just continue that out for however many reactants are involved. So in this particular template, here I have 3 reactants stated, but you could theoretically have 4 or 5 or as many reactants as you want. But usually when you're working with chemical reactions, you don't usually work with more than 1, 2, or 3 reactants at a time. So again, where this k is what's referred to as a rate constant, and the weird thing about the k is the units can actually change quite a bit, but the units for k are such that the right-hand side here and the left-hand side turn out to have units of moles per liter per second. So in the previous lecture, we introduced the concept of molarity, which is concentration per unit volume, and concentration per unit volume, or how many molecules of a compound you have per unit volume. So you can sort of think of this equation as being the rate that the molarity changes is the change in molarity with time, and that's how you can mathematically model how the chemical reaction is proceeding. So if we take a look at an example chemical reaction here, so here I have dinitrogen tetroxide decomposing into 2 molecules of nitrogen dioxide, and then so this two-way, just a little bit of notation, this little two-way arrow here suggests that this reaction is occurring to form this, and this reaction here, the nitrogen dioxide molecules are combining to also form this. So we have at the same time dinitrogen tetroxide decomposing into 2 molecules of nitrogen dioxide. At the same time that's happening, we also have 2 molecules of nitrogen dioxide combining to form dinitrogen tetroxide on the left-hand side. And if we want to express this in terms of the nomenclature that we defined up here, then the rate of this reaction, that is the decomposition of dinitrogen tetroxide into 2 molecules of nitrogen dioxide, the rate would be expressed as the rate constant for that specific reaction times the concentration of dinitrogen tetroxide raised to the power of 1, since the coefficient that appears in front of here is just 1, so that's just the power of 1. We could even leave that out if we wanted to. I chose to include the 1 in here because there is in fact a 1 in front of here. It's just implicit. It's just implied that there's a 1 there. But that's how you would write the what's referred to as the rate law. If I remember my chemistry correctly, the rate for a reaction is the reaction constant, or the rate constant, times the product of all concentrations of all reactants, and each respective reactant is raised to the coefficient that appears in front of it. And as we we didn't actually mention this, but we sort of implied it on the previous slide. It turns out that most chemical reactions are in fact a two-way reaction. That is, you have reactants that are in the process of forming products. That is, the left-hand side of the chemical formula is forming what's on the right-hand side. But you also have products that are reacting to form reactants. You have the stuff on the right-hand side reacting to form stuff on the left-hand side of the chemical formula. And this is what we specifically looked at in the previous slide. You can also think of this in terms of a forward reaction, that is, the rate at which the reactants are reacting to produce products can be expressed as follows, and that's typically denoted, when you write the rate constant for the forward reaction, that's typically denoted as lowercase k sub 1, but other than that, pretty much everything is the same as what we had on the previous slide. And then the reverse reaction is written as k sub minus 1 to sort of denote that this is an inverse. So this forward reaction, that's the rate at which the reactants are producing products, and the reverse reaction is the rate at which the products are reacting to produce reactants. And as you'll observe, if you do any sort of chemistry, you'll see that eventually the forward reaction and the reverse reaction will reach an equilibrium state. That is, the rate at which the reactants are being produced will equal the rate at which the products are being produced. So that can sort of be represented mathematically as the forward rate, that is this entire expression, is equal to the rate of the reverse reaction. And when that occurs in nature, then the reaction is said to achieve equilibrium. So this kind of goes back to the theme that we've looked at so many times before, how Mother Nature doesn't like things to be imbalanced. Nature prefers things to be at some sort of balance. And in the case of chemical kinetics, eventually a reaction will reach some sort of equilibrium state where the rate of the forward reaction equals the rate of the reverse reaction. So again, at equilibrium, that's stated mathematically as the forward rate equals the reverse rate. And if we want to do some more math behind this, so again, forward rate equals reverse rate, and these are the mathematical definitions that we applied in the previous slide, what we can do is we can set these two equations equal to each other so that we get this expression for forward rate is equal to this expression for the reverse rate. And if we do that, we get something that looks like this. And we can do a little bit of algebra here. We can move this rate constant for the reverse reaction over to the left-hand side and move all these the mathematical product of all these reactions over to the right-hand side to get an expression that looks like this. So we have a ratio here on the left-hand side. This is the rate constant for the forward reaction. Again, forward reaction being reactants forming products, divided by the rate constant for the reverse reaction. Again, that's the rate at which the products are reacting to produce reactants. And that is equal to this expression here, the mathematical product of the concentration of all products divided by the mathematical product of the concentrations of all the reactants. And in fact, this left-hand side here, this ratio of the rate constants is typically referred to as capital K, and this capital K is called the equilibrium constant. And this just more or less represents whether in this particular chemical reaction, this represents whether the products are going to be preferred or whether the reactants are going to be preferred. So if this constant is very large, that means at equilibrium, your concentration of products is going to be much larger than the concentration of your reactants. That would imply that this particular reaction favors the products more than it does the reactants. And if you look at this from a mathematical standpoint, if the products are preferred, you have higher concentrations of product. The concentration of products is higher than the concentration of reactants, meaning you have a large number appearing on the other side of this equation, meaning K is large, which implies that the products are favored in the reactants in this particular reaction. And on the flip side, if K is really small, then that means the reactants are preferred. So at equilibrium, and this would imply that you have much more reactant than you do product, which would give you a small value for this capital K, which would imply that the reactants dominate this reaction. You're going to get a higher concentration of reactant than you are going to get of product. So that's going to do it for this first segment, sort of introducing some of the concepts of chemical kinetics. And in the next segment, we are going to take a look at how exactly these concepts can play out in the atmosphere. So with that, I will see you all in the next segment.